the trend line is only looking at the blue dots. It doesn't know the red dots exist.
Okay.
So we'll go back to okay, so any questions and all that? All right, so here's the interesting thing. Let's talk about big data. The formulas behind equals slope and equals intercept assume that you can do a full table scan, that they use every single piece of data you have, and that might take a while if you have big data, right? Especially if your data is broken across multiple machines. You might need to like use the data on this machine, send the results over to this machine, have it add more to it, and stuff, right? So it turns out there is a way to do linear regression in a streaming way, where it just every new data point that comes in, you add it to some of the statistics you've computed so far, and update your estimated slope and intercept. So I've got those formulas implemented here. This will be on the test tomorrow, so I hope you all are good at memorizing.
He's joking.
So it's just to say, hey, look, we can do this. Let's see, anything else to say here? It's just a bunch of like updating formulas. So if you wanted to implement linear regression from scratch for a big data project, you could do this. But you should probably use Spark or something that's already got it debugged for you. Right? Okay, so that's streaming. Now here's an interesting problem. Before I said take gene Q and predict protein H. But now I also have gene activity levels for gene A and gene Q. So how can I use both of those to predict protein H?
Is gene A and Q somehow related, or they just random stuff?
I don't know. I mean, in reality, what do you have? How many people know about a gene chip or a DNA microarray? Okay. So you take a bit of silicon, just like a regular computer chip, and you stick little bits of DNA to it, like 10 bases long. A base is like A, C, G, or T. I don't know if it's 10 bases, 20 bases, something like that. So you stick a whole bunch of these different little tiny strands of single-stranded DNA, and then you take a blood sample from someone and do some chemistry stuff to it and wash it over the gene chip. And some of the DNA from that blood sample sticks to some of the DNA strands that you got stuck to the chip. And then you want to know, well, which DNA strands got something stuck to them, which didn't. So you basically use a laser to see what fluoresces, and you can measure the gene activity levels in that blood sample. How many little DNA fragments are stuck to a chip? Something like 20,000. So when you do this, and it costs like $1,000 for one of these gene chips, last I checked. You get not only gene A and gene Q, you get 20,000 gene activity levels. So we want to put a coefficient on each one to try to predict something like how much protein is this person making, or do they have this chemical in their body or something like that. So we started with just one. Now we're moving to two things, and we want to use them together to predict this other thing.
We can do a neural network and train them using.
We can try that, yeah. This is a very simple neural network I'm suggesting.
Yeah, very.
Linear activation function. Okay, so I already have the formula programmed in here. Just like before, it says take an intercept plus a coefficient times gene A plus another coefficient times gene Q, and that gives me a prediction, and then I compute the residuals, take the sum of squared errors or the mean squared error. Okay, so I could play around with those all day. How do I get the optimal set of them? Well, in Spark, it's just as easy to say, here's two columns, give me this prediction, or give me predictions of this, rather than just here's one column. So in Excel, if you really want to do it, there's a tool called the data analysis tool. But actually, here I'm using a different tool called Solver, where you say, I want to set this cell, that's probably the sum of squared errors, as small as possible by changing these cells, by adjusting the coefficients and the intercept. And is that a linear problem or a nonlinear problem? It's nonlinear because I'm squaring things. So Solver can handle up to 200 variables. It's actually built into Excel, but it's an add-in that you have to activate. Let's see if it's on this. Oh, there it is. Oh, and that is not friendly. Okay. Sometimes Macs do interesting things. All right, well, there's a screenshot of it anyway. So if you want to learn the math of how Solver works, you would take my Math 560 class, not this coming fall, but the fall after that.
What's the name of that class?
Optimization theory.
Oh, okay.
Okay, so that's the idea of now I have two things to predict one thing. And I'm still doing sum of squared errors. All right. So now, here's a real data set. I know some of you have seen this before. This is Pennsylvania schools districts, 2005. What percent free lunch did students in the district get? Like what percent of kids in the district got free lunch because they were below the poverty line? What was the average teacher salary for full-time teachers? And what was their student-teacher ratio? And we want to use these three things to predict their test scores on a math test in 11th grade. So here I have a plot of for each school district, what percent of their students get free lunch, and what math test scores do they tend to get in that district. And what do you notice about this plot?
The more percent get free lunch.
Yeah. The lower the test scores go. The obvious thing to do is cancel the free lunch program, move all these points back up this way, right? Whatever is in that lunch is not good for grade sets. Seriously, what's really going on there?
McDonald's.
No, it's not McDonald's. It's poverty, right? Who gets free lunch? Kids who are living in poverty, and poverty is bad for learning, right? How do you measure poverty in a school district? Actually, the standard way to measure it is what percent of kids get free lunch. So that's how free lunch predicts things. We could also say, how does teacher salary predict things? Oh, look, pay teachers more, see better test scores. Hard to argue with that. Well, maybe that has to do with cost of living and real estate prices and stuff.
Yeah, teacher in a an area with less poverty, you'd probably paid more than.
Yeah, probably. And then here's the surprising one. How about bigger classes? What do bigger classes predict? So this is student-teacher ratio.
Not much influence.
More students.
Kind
More
of flat.
students. More students actually goes with higher test scores, which is weird. But the R-squared is very, very low. So there's basically no effect there. But that's three different regressions rather than running it all at the same time. So this is teacher salary without compensating for what percent of students get free lunch. So we'd like to run it all together. So the next thing is using this tool called a regression analysis. And hopefully I can actually do that here. This is a screenshot of it, but let me show you how it works. Data analysis, regression. And I'd have to say, what's my Y range? What am I trying to predict? I'm trying to predict test scores. What's my X range? What am I trying to use to predict test scores? I'm trying to use percent free lunch, teacher salary, and student-teacher ratio. I told it what the labels on the columns were, like the little word above each set of numbers. And we'll put that in a new worksheet. You should usually do these. So I just put a new worksheet here. It's the same as what I have over here, except here I've got a screenshot of the dialog box I just used. So it gives us an R-squared value. .477, is that a decent R-squared value?
It's not so good.
If you were designing a bridge I was gonna drive across, or like a nuclear power plant I was gonna live near, or an airplane I was gonna fly on, I would want much better values there. But for sociology, biology stuff, that's actually pretty decent. So it all depends on the field you're in and how predictable things are in that field. So we get R-squared of .477, and we get an intercept and a coefficient on each term. So I could use that to go back and make predictions. But I've also got this highlighted. How important is percent free lunch? How important is teacher salary? How important is student-teacher ratio? Can I say, well, look, this coefficient is negative 268. This one is .0023. Is this one massively more important than that one?
So does is the importance indicated by the coefficient or by the p-value?
No. Neither one is true. Yeah. Yeah, the coefficients, like what's the units of percent free lunch coefficient? It's test score points per percent free lunch. What are the units of this coefficient? It's test score points per dollar of teacher salary. But dollars of teacher salary are in like the 50,000 range. And so it makes sense that this is a pretty small thing because it's being multiplied by 50,000, 60,000. This one's getting multiplied by like 10%. Not even sure if that's a decimal, like 0.1, or if it's literally 10. It's probably 0.1. So you can't even compare these numbers because they're in different units. So you can't just look at these. And this is actually an important lesson for later when we get into other machine learning stuff. These coefficients are in different units and they're not comparable at all. We can look at these p-values. If you've taken a stats class, you've heard about hypothesis tests and p-values. These are those. And it tells you how certain are we that this coefficient, that's not exactly the question it answers, but it's trying to tell us, is it plausible that this coefficient is 0? If the coefficient is 0, that means that that element is not very important. And so these have a very low p-value. They're strongly statistically significant. But this one, it's not below 0.05, and so it's not statistically significant. So that's saying these coefficients are plausibly important. This one, maybe not so much. So it's a way of selecting variables to say, well, which variables are really important? Is selecting variables important when you have big data? Yeah, because you might have a billion rows of like, how many customers does Facebook have? Probably in the billion range.
Like 1 billion.
Okay, so if they had a row for each customer, that would be a billion rows. And if they're trying to predict like how much money they'll make on you next year, what do they have to predict that? They have clickstream data, right? What did you click on? What have you liked? And so there could be like, did you like CNN.com? Yes or no? Did you like FoxNews.com? Yes or no? Did you like this website? Yes or no? Right? How many columns do they have? Tens of thousands? And they want to weed out, well, which ones are important for us to use and which ones are not really important. So it's important to be able to tell which columns seem to have some predictive use and which don't. So that was just using these three things: percent free lunch, just teacher salary, and
I
some
think
teacher
the
wages.
sex of a customer is
Okay, yeah.
random, right?
And
Not pretty fancy.
okay. What else could you do? Like, have they uploaded a profile picture or not? That might be important. How many times have they posted in the last 5 days? All kinds of ways you can imagine measuring customers. All right, so that was using those three variables, which make a lot of sense. Here's another regression where I used those three variables, percent free lunch, teacher salary, and student-teacher ratio. And I also use the district number. Back here, we have 500 districts. So while I was highlighting stuff, instead of just highlighting those, I highlighted this. Do you think the district number will help me predict student test scores?
Nope.
That would be a really weird numbering system that helps predict student test scores, right? But let's look at the output. Let's look at the R squared. R squared is now 0.479 instead of 0.477. R squared went up. So now I can make better predictions now that I'm using the district number as well. So is that good?
Nope.
It's counterintuitive.
It's counterintuitive that I included a column that should not be informative at all, but now I can make better predictions. Okay, well, if a little is good, more is better. So let's try this 6 variable output sheet. Look at R squared now, it's 0.48. It was 0.479, now it's 0.48. And what other 2 columns did I include? 2 columns of completely random numbers. Over here, it's rand 1 and rand 2. The formulas aren't there anymore, but they're just uniformly random between 0 and 1. So this is good news, right? If I want to impress my boss, I can say, hey, look, I made R squared go up. I just create a bunch of junk columns and throw them into the regression along with everything else. Or maybe that's not the best idea. So how can I weed out columns that don't really mean anything? Well, I can look at the p-values. These p-values, well, that one's below 0.05, so that would actually typically get included. I didn't even engineer that to happen. But there's another way to say, well, does adding this column really help my regression all that much? And that's this other number right here, adjusted R squared. So if you add a column of junk variables, adjusted R squared will stay about the same. It won't be exactly the same, and sometimes it'll go up a little, sometimes it'll go down a little. But it's like a 50% chance it'll go up, 50% chance it'll go down. So if I compare adjusted R squareds across these models, 0.474, 0.475, so it went up a little bit. Went up a little bit, but not as much as the other. Yeah.
How do you calculate the adjustment?
You use this tool in Excel that calculates it for you. I don't know the formula, but it's basically you take the R squared and subtract something about the number of parameters you're using, the number of columns, and you like divide by the number of data points or something. So it's a really simple adjustment saying the more parameters you include, the more I'm going to subtract from your R squared, because we expect R squared to go up when we add any column, whether it's useful or not.
So it's kind of trusting that everything you include has some informative
R
value.
squared is, and then adjusted R squared is trying to say, hey, but wait a minute, we know that adding a new column that's not informative can still make R go up. The reason R goes up, here's a question. If you were going to run, let's say, a mile, would you rather run the mile the way you are, or run the mile with one arm tied behind your back?
The way we are.
I'd rather run it with no restrictions, right? So, I mean, you don't think it would make that much of a difference, right? But here, I did a model with 6 parameters plus the intercept. When I did the model with 3 parameters, you know what? I was actually doing a model with 6 parameters, except the other 3 got set to 0. Right? Doing a model where I only give it 3 columns is saying you are not allowed to use these other 3 columns. It's giving it a restriction. And so when you take away that restriction, and now it can use those columns, it can put some little coefficient on it to make things a better fit, but it doesn't really mean anything. So fitting a smaller model is fitting a restricted model compared to the big one, and adding restrictions makes things worse.
So when we compute R, we need to know the actual values and the predicted values.
Yeah.
So for all of these things, you have somewhere the actual values.
Right. So for all of these, I'm using the actual values here.
So when you added that a few random columns, it was able to better fit the curve to the actual values.
Right. It's actually it's a straight line, but yeah, it could be.
This is straight up, okay.
Yeah, so it's now able to throw in, and I said you shouldn't pay attention to coefficient size, but these are relatively little coefficients in the grand scheme of things. But because before, when I didn't include those columns, it was basically setting these to 0 and say you must zero out your attention on those columns. So one way to say, let's get rid of junk columns in the regression is to say, well, let's look at adjusted R squared, and if that goes up when I add a column, then that column was probably useful. So that's a straightforward way. It's not the best way, but it is a way that people look at things. Yeah. Okay.
Can you explain a little bit math, the reason why when you restrict your arm, it will get worse?
So it's a general principle that the more restrictions you put on things, the worse things get for whatever you're optimizing.
Really?
Really? Yeah. Like, well, let's say I'm a business and I want to make a maximum profit, right? The way to make a maximum profit is instead of hiring 2 people that each work 40 hours a week plus benefits, hire 1 person, make them work 80 hours a week, and then I don't have to pay 2 packages of benefits, right?
Okay.
So that optimizes my profits for that week. Is this a good idea in the long run? Probably not, right? I'd have to retrain someone after someone burns out. Okay, so if you're telling me that in the long run that's like illegal or something, to make someone work that much, except for doctors, we can make them work that much. If you're telling me I can't do that, that I have to hire 2 people at 40 hours, my profits go down because I'm now spending more money. Right, so anytime I have an optimal solution, you come along and say, no, you can't do that because of this. Like if I'm routing airplanes and I find a way to save a lot of money by taking this one airplane, sending 40% of it to California and the other 60% to New York, and you come back and say, no, airplanes have to be integer, then I can't do my solution anymore. I have to change solutions. But my old solution was optimal, so my new solution will not be optimal. But it will at least keep the airplane all in one piece. So another way of saying which columns are useful and which are not. There were quite a few other questions. No, okay. Never trust me to route your airplanes, by the way. Another way of saying what's a useful thing and what's not. I'm going to switch to the display camera here. Is something called lasso. It stands for least absolute something and selection operator, but it's not important. Shrinkage and selection. So what we're doing in ordinary regression we're saying minimize the sum of squared residuals and we like taking the mean, so we'll divide by the number of data points. So that's ordinary regression. I just want to come as close as possible to the data points that I have.
You mean this is like the goal of ordinary, or is it the measure of its accuracy?
So the measure of accuracy is that, without the minimum. And I want to get as accurate as possible. So I want to find the parameters that minimize my measure of how far off I am. Accuracy, usually higher accuracy means lower residuals. So I want to minimize residuals to get the best accuracy. Okay, so that's ordinary regression. And then for lasso, I want to say, I want to try to ignore columns if I can. If a column is not important, I want to set its coefficient to 0. So I throw in another term, the sum of the absolute values of each coefficient. Don't need both variable like that. So that says, hey, look, if a coefficient is big, it's hurting my overall sum. If a coefficient is 0, then it's not affecting my overall sum. So this is giving me incentive